My name is Travis Rappley, and if you don't already know me, I am a project management consultant. But much more than that, I've spent my career in startup MedTech companies, doing a variety of functions in R&D operations, and uh, and and mostly in project management, but in early stage product development. And one place that I see us struggling a lot is in design verification, and specifically related to design verification planning. And so I thought, let me walk through what I think is a, a good approach to get design verification planning done at the right time. Let's see here, my PowerPoint is stuck. Okay, so what I'll do is I wanted to just kind of walk through the process of design traceability, so that we've got the good baseline on that, and then show how I tie it into design verification in a unique way, but it's not too much trouble, and I think it's a really good way to go. And so I wanted to use the example of a replacement knee. This is a striker triathlon knee, and I wanted to walk through, use it as an example to walk through the design traceability process, and then switch gears to how we can use what we're doing already in the design traceability process to plan design verification. And the first step in design traceability is establishing user needs. In case you're unfamiliar with that, this is the starting point for development of a device. It's some physician or somebody that's got a problem that needs a solution, and what they need from the solution, we write out in a list of user needs. And so a typical set of needs for this knee that a physician would tell you is something like, it's got to last more than 10 years. It's got to support average body weight. It's got to allow bony ingrowth for the bone contacting surfaces so that it stays put. It can't dislocate under normal use conditions, and it's got to be biocompatible. There's going to be a much longer list of user needs that we end up with, but this is an example that I came up with for the artificial knee replacement. This is pretty straightforward. This is through attending conferences where physicians are gathering to talk about the latest and greatest. That's a good place to meet a bunch of physicians. Reach out to contacts, internet searches. There's all sorts of places to gather these user needs, but this is step one in development of a device, is gathering these user needs. And then the next step is something that I think just across the industry we could do a better job at explaining and getting down, and that's something called design inputs. It's another way to word design inputs is design requirements, and this is just taking our user needs and putting numbers on them. So, and wherever those numbers come from, it's a variety of places again, but we'll have our list of user needs, and from that we establish design input, design requirements. And so the process is, you take a user need like must last greater than 10 years. I looked it up, and the average human walks 2.5 million steps per year. That's something that's easy to look up in literature, or just you can Google that one and multiply that by 10. I got that was easy math to come up with 25 million cycles. And we do that for every user need, but what we end up with in doing so is a set of requirements that we can actually design to. In the list of user needs, that may not have the information that we need to go out and design our device. Or if we do go out and start inventing our device or designing our device based on user needs, what will often happen is that there's a lot of extra trial and error to get the product right. And we can waste a lot of time and money trying to design straight off of user needs. So we have this interim step. It happens to be required in the FDA regulations, which is handy. We're doing it anyway. So we take each user need and convert that to a design requirement through research. You can ask physicians for their expert opinion. You can collect data yourself. If you don't have some of this data, or it's not available readily, you can gather this from cadaver testing even live patients, whatever we need to do to get these design inputs. And this would, and you can see here that we take something like must support average human body weight. I don't know what that means, but when I look up the average human weight, I can see that, oh, there's maybe a maximum of 250 pounds or something reasonable. We do that for each one of the user needs, convert it to a tangible design requirement. Allows bony ingrowth is something, again, that a physician would tell you that the product needs to do. And then through literature, we can find that, oh, that means it's got to be a porous surface, and the openings should be 100 to 400 microns in diameter so that the bone can grow into the substrate. Great. We do that for all of the user needs and come up with these design requirements. These actually help us to then go to design our device and make sure that we're designing the right device that's going to meet all of our user needs. So then we do our design work. Here's where the inventing comes in, right between design input and design output. We take our design input, we start brainstorming and coming up with ideas, prototypes, solid models that would potentially meet all of these design requirements. We maybe go through a couple cycles of design, prototyping, testing to come up with our design outputs. And so once the design work is done, we have another column in this design traceability called design output, which are our specifications. Again, these are required. It's required that we list these per the FDA regulations, so that's handy. We're already doing it. And you can see here how we connect the dots between, we've connected the dots between user needs and design input prior to this, but now we've taken a step further and connected each design input to a specification of the device that we ended up creating. And so here's an example of a list of design output. It would be that we made the product out of cobalt chrome and polymer that are designed to exceed 25 million cycles. Same thing with design specifications and drawings to ensure that we have a product that exceeds 250 pounds of load. And on down the list, we've specified a certain porous titanium coating made by a certain process that's designed to ensure 100 to 400 micron pores throughout. The design of our device it ensures that it's got a greater than 75 Newton tensile strength. That can be done through modeling in SolidWorks and then finite element analysis or some sort of assessment straight in SolidWorks that we can reasonably guess that the design that we come up with exceeds 75 Newton tensile strength from that. And so this is documenting our design in 3 steps, going in stepwise from the physician giving giving some input into what their needs are, but not getting specific about the detail. We dig up the details and establish design requirements, design input, list them right next to the user needs. And then once we've invented our product or designed our product, we have a list of design outputs, which are specifications. And then the final piece of the puzzle is, how are we going to confirm that the output meets the input? We do design verification testing. And so there's another column here on the right where we've taken each design output and determined a test that we're going to do that ensures that we're going to do this testing and ensure that the design output meets the design input, and we have one for each one of these rows. And so putting this all together, this is something we always do. I'm just kind of giving a little bit of a background in case anybody needed some refreshment on this. We put this all into a traceability matrix. This isn't required by the FDA, but a lot of people do it. A lot of companies will put together a traceability matrix to keep all this in one place, and it'll look something like this, where we've got a row for each user need, the associated design input, the associated design output, and the design verification. And this is fine. This is what we end up with most of the time, but there's, with a little bit of extra work, this could alleviate some problems that we run into. And here's the problem that we face, not because of this, but just a problem that we face in the industry is this is a schedule of how design verification should ideally go, where we've got some product design work happening in parallel. We're doing some design verification planning. When those two activities are complete, or when the design work is done, we go order components, do some more prep work for the design verification that's coming up. There's test fixtures for custom test methods that we have to design and fabricate. There's manufacturing documentation for sure. There's always, before we can do a design verification build, there's always manufacturing instructions that need to be created or finalized. The test method and design verification protocol itself is ideally done during this time. And so in an ideal situation, we've got a chunk of time for product design. At the end of product design, we're starting to do our design verification planning. And when we order components, we use that time to do the rest of the prep work for design verification. This is how, in an ideal situation, things would go. When the components arrive, we're done with our fixtures, our test methods, our documentation. Everything is ready to be put together into a design verification build. You can see down here on this line where my cursor is. And then once the build is complete, mechanical testing. We've always got some sort of a long lead test. Biocompatibility is a big one. There are other tests. Even in this case, I didn't highlight it here, but the wear testing can be lengthy. The fatigue testing can be lengthy. We've always got something that's longer in duration than other design verification activities, but ideally we would organize it such that the long lead testing isn't on critical path. The critical path here in this whole process is outlined in red. You've got product design, order verification components, design verification build, and the testing should ideally be on the critical path. And critical path, usually what I try to do is only have things on there that are out of my control. And something like biocompatibility testing, I should be able to get that started one way or another early and keep it off of my critical path. But what often happens, more often than not, is that we are busy with design. There's all sorts of things happening at the end of the design cycle where we have unanticipated cycles of design where maybe we got behind in design for manufacturability and we have some changes at the end. We tend to get so wrapped up in finalizing the design and keeping this design phase review on track that the verification planning is neglected. And when we neglect the verification planning, it pushes a lot of things out. One of the biggest things is a second component order. If we haven't done design verification planning, meaning outlining all of our tests that we're going to do, how many samples, how long each test is going to take until we're done with the design work, then we might realize once we're done with the design work and we've got our drawings, we order our components, and then we take our time to do design verification planning, we often find out that we've under ordered, and then it leads to a second order. And that's where this sort of snowball happens, where once we realize we need more components and place that second order, now we're kind of scrambling to get the order delivered as soon as possible so that we don't lose that much time. We're expediting the order. We're maybe taking in and using some non-conforming parts. At the same time, we've compressed the amount of time that we have to do all the other prep work too, like design and fabricate test fixtures, finalize manufacturing documentation, get the protocol written and released. All of that stuff is pushed forward because we haven't planned until we've got our design in our hands. And it pushes a lot of this work forward unnecessarily. You can see here, it pushes something ridiculous onto the critical path like biocompatibility, which shouldn't be. The build is pushed out. Everything is shifted because we are just, it happens. We're so busy with the design work that we neglect the verification planning until late. And I have a way that I love to pull the design verification planning back in earlier and keep everything closer to the ideal situation like this. And it's marrying the two things that we're doing anyway, which is what we already talked about, the design traceability exercise we're already doing anyway. We're already doing design verification. It's just how do we avoid planning late? The way I like to do it is just add a little bit of a detail to our friend, the traceability matrix that we're already creating. We've got the user needs, the design inputs, the design outputs, the design verification. These 4 columns are standard. This is a very typical snapshot of a traceability matrix. But what a lot of people don't do is on the end of it, if whether you add a column or add detail to the design verification column, if as you're going and creating this traceability matrix, you add the actual verification information in, even if it's a guess, it helps everything. It helps smooth everything out. Here you can see I've added some details of the type of data that comes from the test, or that the test collects, the sample size, whether it's destructive or not, the duration of the test. If you just put some very basic information about the design verification activities that's not already in a typical matrix, it helps smooth everything out. So when I add this detail here, if I'm completing the traceability matrix sometime, start it, we're doing it anyway, and it's going to be due by the phase review. If we start it sooner and add that detail, it helps us with this design verification planning, put it where it's supposed to be in overlapping with the design cycle. So starting it earlier than at the last minute for the phase review, and then adding some testing details really makes it a powerful design verification planning tool that put this the design verification bar planning activities where they should be. It's real simple. We've already got this document anyway. Adding these details helps me to see things like how many samples do I need to build. That really helps with component orders, so that we only order, place one order. We can use accommodate standard lead times, standard pricing, because we know how many that we're going to need and we've ordered enough ahead of time. That is one area where consistently I see companies and teams sort of misstepping, is not ordering enough components and not ordering them at the right time. Having a somewhat reasonable idea of our design verification up front earlier on in the design process helps us with that. We can see how many samples we're going to need to build total. This one here is non-destructive testing, so I know that this design verification test, this helps me with the flow. This design verification test is going to come first, because those parts can be analyzed optically. We can get our data, but then the samples haven't been manipulated. They can go on to other testing. We can identify the long lead tests and start to plan before we're done with the design of our device. We can start planning for addressing these long lead design verification activities. We can get them started earlier, or just know that we're going to have this chunk of time that's unavoidable. Either way, all of this stuff is being revealed earlier on in the process by just starting this traceability matrix earlier and adding the testing details. It gets us back to where we want to be, pulling in the design verification planning earlier. It smooths out everything when all of the above, everything we've been talking about. Ordering the design verification components. When we place that order, we've ordered the appropriate quantity of them. We can accommodate standard lead times. We don't need to place another order for components and expedite it and work, possibly, like I said, accept non-conforming products. We have time to do the other prep activities because we've already done the planning and aligned it with the phase review, the end of the design cycle. We can switch gears to ordering components, doing the rest of the prep while those components are on order, and be set up to conduct the design verification build on time when the components come in, complete our mechanical testing, keep long lead testing off of our critical path if we can. It kind of alleviates all of those issues that are extremely common issues for design verification. It's more common than not to feel frantic and behind all the way through design verification. And with just a couple of tweaks to something we're already doing in the traceability, we are able to pull that design verification planning in. Part of the problem is in design verification planning isn't horribly well described in a lot of design control procedures. And in lieu of a design control procedure that requires design verification planning in a structured way at a certain time, this is the next best thing, is just kind of take a tool that we're already using, the traceability matrix, modify when we're creating it and how, and the information we put into it a little bit, and it gives us everything we need. It gives us our wish list of design verification planning earlier, therefore enough room to do the rest of the design verification prep during our component orders. And that was it. So just bottom line, take your traceability matrix, start it earlier before the phase review, add a little bit of testing details, and it makes everybody's life easier. Supply chain is happy because we don't have multiple component orders with expedite fees all over the place. Obviously the finance team is happy because we're staying within budget. Manufacturing is happier because we know when the design verification build is coming. We've got all of our documentation prepared ahead of time. The test labs are not scrambling with rush orders and expedite as well. I think it makes everybody's life easier if we do the design verification planning, pull that in just a little bit. We can save everybody headache, expense, and time doing that way. I am not able to interact. Let's see here. I'm not able to interact through the LinkedIn Live. So I apologize for not being able to field any questions, but here is my info. Please scan the QR code and connect with me on LinkedIn if you aren't already. This is my first of a series of webinars that I plan to do this year. So I'm doing another one in May, on May 8th. Tune in on my LinkedIn page for details about that. I'm doing a longer design controls basics workshop it'll include this information, but a lot of other design control 101 type information and activities on June 4th. That's going to be in person at the Oregon Bioscience Incubator in Portland. So if you can make it out, it would be awesome to have you. If you're local to Portland, even better. That's going to be a fun one for anybody who is new to medical device development, and maybe you've got some sort of a non-technical background, like a physician background or a marketing background or a business or sales or something like that. If you find yourself in a product development environment and sort of need to get your bearings, this will be a great workshop to help through all of that. We're going to have activities so that you can have some hands-on contact with all of the non-business related activities that we do when we create products in medical devices. That's on June 4th. So follow Oregon Bioscience Incubator, follow me on LinkedIn. You can reach out on email here. Here's my LinkedIn page, and I've even got a website. I would love to hear from you, and I would love feedback on this webinar, but then also, unfortunately, since I'm streaming it live and I haven't done this before and I can't interact, if you have any questions, please reach out to me. I'm happy to elaborate, clarify, share my slides, all of the above. I'd love to hear from you. So thank you very much for tuning in.